Okay, awesome. So welcome everyone to the Pure Math, Applied Math, and Combinatorics Combinatorics and Optimization Club's presentation. I'm happy you could come out, and let's get started. So first, let me introduce myself. I'm Spencer Wilson. I'm in my 4th year of computer science and pure math, 4A in Waterloo language, which just means first half of 4th year. I'm from Orillia, Ontario originally. I was homeschooled in high school. I'm doing, as I think I said, I'm doing a degree in computer science and pure math, but I'm also picking up Spanish along the way. So I'm hoping to graduate with like a Spanish language diploma. I'm super passionate about cryptography. I've taken a few courses in it. I've worked with it in industry, and I'm doing a master's in it after I graduate. So I'm really excited to share that passion with you today. I should also introduce my club because it's through the club that this talk is being given. MathSoc is arranging presentations by each of some of the main clubs to students. So we are the Pure Math, Applied Math, and Combinatorics and Optimization Club. Most people call us the Pure Math Club or the PMC for short. And when things are in person, we organize a bunch of cool in-person events, including Prof Talks, which are hour-long fun lectures by Waterloo math profs on fun topics in math in an informal setting. We also organize student talks, which are short attention span math seminars where anyone can sign up and give a 20-minute math talk. And we organize a few contests as well. My personal favorite is the over 9,000, where you make teams and you're given this weird mathematical quantity and you have to guess whether it's over or under 9,000 in a certain time frame. And of course, we have free food at all of these talks and events. So a lot of people show up for free food. Some people show up for math. We have also been hosting a few of these events online in the past couple of terms, and we're amping that up recently. So whether or not we're allowed to have in-person events in fall, you should come check us out when you get started at Waterloo. And we also have a Discord server and in-person office, so it's just a fun place to chill and hang out with friends who also like math. So this talk is going to be really chill and informal, I hope. I just want to share a cool application of math with you that I really like, and I hope that you'll learn a little bit of something and maybe see how math can be applied in ways that you might not think of. It's not like you're not going to be quizzed on the content, or it's not a lecture, so there's no pressure to answer questions. I will be asking questions, but that's mainly just to keep it sort of interactive. And if you don't feel like responding, no pressure to, but it would be nice if you did. This next note I left in before I knew that we had to record the meeting. I was going to ask people to turn your cameras on if you're comfortable with that. It would still be great if you're comfortable with turning on your cameras, given that it's being recorded. That's up to you, obviously. It just helps me. Oh, hey, Maya, thank you. It just helps me to know how the presentation is going and when I need to slow down, speed up, ask for questions. But if you're not comfortable with that, I understand. If you have a question, just raise your hand in Zoom. There's the raise hand button at the bottom, I believe. You can also type it in chat. I'm a little less likely to see it if you type it in chat, but if you raise your hand and then unmute and ask your question. If you can't find the raise hand button or the chat, feel free to just unmute and shout it out. It's a small crowd, so it shouldn't be an issue. Please don't be afraid to ask questions. This is, just informal and fun and interactive. So ask away. Okay. With all that said, let's get started. So we're going to talk about cryptography. So before I start telling you what cryptography is, oh, I see there's a message in the chat. Okay, never mind. Sorry. Before I tell you what cryptography is, I should ask if anyone knows what cryptography is already or has ideas about what it is. Any takers? I see some thumbs up from Maya, but I'm fairly sure Maya knows. Oh, hold on a second. Sorry. When somebody raised a hand, I think it kicked me out of full screen. Okay. Yes, David, go ahead.
Like when you encrypt stuff for privacy reasons.
Yeah, that is very good. That's one aspect of cryptography. Encryption is a part of it. Cryptography does a lot more besides encryption, but encryption is sort of the main thing that people think of when they hear cryptography. Awesome. Yeah. So cryptography is all about who can do what with data. It's hard to sum it up in one definition. So it's easiest to talk about it in terms of its goals, what cryptography is trying to achieve. So the first of those goals, which is the one you probably think of, is confidentiality. That's keeping messages that are supposed to be secret, making sure that only people who are allowed to read messages can read them. So if you're making an online purchase at Amazon or another site and you send your credit card information over the internet, the job of cryptography is to make sure that only you and Amazon or whoever you're making your purchase from can see that credit card information. Nobody along the way who intercepts your transmission should be able to read it. Today we're mainly going to talk about confidentiality, but you should know that there are other roles of cryptography, including data origin authentication. That is who can do what with data. No, sorry. That is when I get a message, how do I know it came from the person who it says it came from? So if my friend sends me a message on WhatsApp or Facebook Messenger, cryptography's job is to guarantee that the message comes from my friend and not from some person pretending to be my friend. Then there's also data integrity, which is guaranteeing that along the way, nobody inserts data and tampers with a message. So if my friend sends me a cat picture on WhatsApp, cryptography guarantees that nobody has modified that cat picture before it gets to me. And then finally, non-repudiation. In some situations, cryptography seeks to provide guarantees that parties can't deny having sent a message. So this is maybe a digital contract. You want someone to be able to, you don't want somebody who signs a digital contract to be able to deny signing the contract, and cryptography has a rule there. David, I see your hand is still up. Do you have a question?
No, I put it down a while ago. Not sure. That might be
okay.
a visual glitch.
Sure. Cool. Okay. So cryptography is a branch of mathematics. And so cryptographers want to have mathematical proof that these properties hold. It's not good enough to just say, yeah, we think they hold, but we want to actually prove things about these properties given our systems for doing cryptography. So are there any questions about cryptography and these goals? Anything I need to explain a little further? Okay, awesome. Let's proceed. You've probably used cryptography more than you realize, because every time you go to a web page that starts with HTTPS, and I think most web traffic now will be HTTPS, there's cryptography going on in the background to protect your data. Your connection is encrypted so that only you and the website can read it. So cryptography also has a really interesting history. Modern cryptography sort of began in World War II with the efforts of Allied code breakers who were working on breaking German ciphers, one of which you probably have heard is Enigma. And if you've seen the movie The Imitation Game with Benedict Cumberbatch, you'll know that Alan Turing, a British mathematician, was instrumental to the efforts of the Allied codebreakers. This is a picture of Turing when he was 16, so presumably when he was just going into university. There's actually also a Waterloo connection with the code-breaking efforts in Britain in World War II. William Tutt was one of the code breakers there. He helped to break I believe, the Lorenz cipher. And he came to Waterloo and Canada after World War II in the 1950s, I believe. And he went on to found the Combinatorics and Optimization Department at Waterloo, which is under the Faculty of Math. And to this day, cryptography research is under that department. And all of our cryptography courses are offered by that department. So Waterloo indirectly is related to breaking German codes in World War II. That's pretty cool. Any questions about the history? Okay, awesome. So now I want to completely shift away from our digital world and talk about the Lord of the Rings. First, can I have a show of hands here? Raise your hand if you've read The Lord of the Rings or seen the movies. Okay, I see one person has. Nobody else? Oh, two people have. Okay, awesome. Okay, cool. Anyway, this is not something you would actually see in the Lord of the Rings books or movies, but I'm hoping that it will be an interesting way to explain things. So here we have two Lord of the Rings characters who want to exchange secret messages. So they're at some big council meeting and they're talking about how they're going to destroy this ring of power, and they want to be able to send secret messages back and forth. So how do they do it? They might be hundreds of miles apart in different kingdoms in the world, and they can't speak directly. So you can see their dilemma here. They can't just shout. So what do? Okay, well, here's the most basic option. They just like write down the message and get some guy on a fast horse to take the message from one person to the other. Now, there are problems with this because, like, what if the guy on the horse gets attacked by evil forces and the message is stolen and the rider is kidnapped? And then the message could be intercepted by evil forces and read, and it wouldn't be a secret anymore. Well, one way around this would be to have like an army to escort the courier, but somebody's always going to have a larger army, so that doesn't really work either, and the message wouldn't be a secret anymore. So this doesn't work. So what could we do? Well, we're going to sort of encrypt the message. So when you don't know what to do and you're in a magical kingdom, you can go to a wizard, and the wizard will usually be able to solve your problem. So our characters here, Aragorn and Bilbo, will go to the wizard Gandalf. And Gandalf makes them this magic box. The box is made of an unbreakable material, and the only way to get its contents is by unlocking it with a key. So Gandalf gives them the box and the key, and then they can use this box and key to send secret messages. So I should pause and ask if anyone has any questions about what's going on, or if there's anything I need to elaborate on a little more. Any confusions that need to be cleared up? Awesome. Okay, let's continue. So the way this box works is you put your message inside the box, you lock the box, and then you send the box to your friend. Like so. Box is locked. Then your friend, when they receive the box, opens the box with their copy of the key and reads the message. If they want to send a message back, they drop their message in the box, they lock the box, they send the box to you, you unlock the box, you read the message. And if the courier carrying the box is intercepted en route, it doesn't matter if the box is stolen, because this box can only be unlocked with the key, and whoever intercepts the box won't have a copy of the key. So it's good, right? Nobody can read the secret message. Does anyone see any problems here? Any issues? Anybody have any questions?
Jay had a good idea in the chat.
Oh, awesome. Thank you, Maya. Let's see. So Jay says, you can't smash the box open. No, this is because it's made by a wizard. This is an unbreakable box. Now, that is a good point. If you would have to be very careful when making this box, because if you made a box that could be opened by a way other than the key, it would be a problem. But in this case, we're assuming that the box is unbreakable. Great point, Jay. Also, sorry I missed the chat. I didn't see the little red button or whatever it is. Okay, awesome. Let's continue. So the main issue here is that in order to set this up, Aragorn and Bilbo needed to be in the same place at the same time to exchange their, like to get the box and trade copies of keys. Now, Aragorn might want to be able to send messages to people who he wasn't in person, like wasn't in the same room as, and they can't have copies of the key right away. Does anyone have any ideas for how he could do this? Any takers? Okay, well, one thing's for sure. He can't just send them the key, because that's like trying to send them a secret message. It could be intercepted. So we're going to have to go back to the wizard and see what else he can come up with. So they go back to Gandalf. Oh, okay, Jay says, tell the message to a bird. That's a good idea. So that would be an alternative. However, the disadvantage of doing that is you're then trusting the bird. The bird knows your message. That's if you're comfortable trusting the bird, you could do it that way. In this case, though, we don't want to trust anybody. But very, very good suggestion. Thanks, Jay. Okay, so Gandalf's newest contraption is a bigger box, and this box has 2 locks, 2 keys, and a trapdoor. The keys are different. One lock is at the top of the box, one lock is at the bottom of the box, and the trapdoor is in the middle of the box. And I'm going to show you how this box works. So to put a message into the box, you unlock the top of the box with the first key, the key to the top of the box. You drop your message in. The message will fall through the trapdoor. The trapdoor only hinges downward. So, downward, does that sound right? Anyway, the trapdoor is one way. When something falls through the trapdoor, you can't retrieve it. So when you drop your message in, it goes to the bottom of the box, and there's no way to get it from the top of the box. To retrieve the message, you need the key to the bottom of the box. So you open the bottom of the box, the message drops out, and you can read the message. Does anyone have any questions about how this works? Is there anything I need to explain a little more or clear up?
I have a question.
Yes, go ahead, Maya.
So how does the person sending the box know to have a lock that fits the key that the other person has?
How does the person sending the box know to
Right.
have a lock that fits the key the other person has? We'll get into that in a minute. Great
Oh boy.
question.
Okay.
Any other questions? Okay, awesome. Let's continue with our box. So in order to send a message in the box, to get to the point Maya raised, it's a little more complicated because you actually want the keys to be with two different people. So the way it works when you're sending messages with this box is Aragorn sends a courier to Bilbo with just a plain text message. This message is not a secret. And he says to Bilbo, send me your big box and the top key to that box. So as a refresher, this is the box, and the top key is the key you use to open the box to drop messages in. The top key won't help you get messages out. So then Bilbo sends the box to Aragorn along with the key to the top. Aragorn uses that key to unlock the top of the box, drop a message into the box. He then locks the box and sends it back to Bilbo. Aragorn can also send his own box with its top key to Bilbo so that Bilbo can reply to his message. Aragorn will keep the top key so that he can send more messages to Bilbo later. But the key thing here is that Bilbo sends the box with the key, Aragorn unlocks the box, drops the message in, locks the box, and sends it back to Bilbo. Then, when Bilbo gets the box back, he performs this step. He unlocks the bottom of the box with the key number 2, which he still has and which he did not send, and retrieves the message. He can then respond to Aragorn using Aragorn's box if Aragorn sent it along the same way. So I know that's a little complicated and it might be a lot to unpack. So does anyone have any questions? Is this not clear to anyone? Anything I need to explain a little in more detail?
Jay's question in the chat, so there's only 2 keys in total.
Awesome. Thanks, Maya. Yes, there are only 2 keys in this case. There's one to open the top of the box, one to open the bottom of the box. You use the key for the top of the box to drop your message in, and then somebody else would use the key to the bottom of the box to take the message in. Yeah, only 2 keys. If you have multiple boxes, oh, I see. I think Jay might be asking about if each of them has a box. Right. There are 2 keys for each box. Not just 2 keys total, but 2 keys per box. So if you have only one box, there are only 2 keys. But if you have 2 different boxes, then you'd have 4 keys total. Yes. Great question. Thank you. Anything else?
I have a question. So
Yes, go ahead.
what happens if the box is intercepted by something else? Someone else?
Great question. So if the box is intercepted, then it's locked, and without the key to the bottom of the box, nobody can retrieve the message, right? Hopefully, that's what we want. So yeah, it's as secure as the previous box. It's locked, and it's also made of this unbreakable material. So we're good if it's intercepted. Great question. Thank you, Valerie. All right. Any more questions? Anybody see any problems with this setup? This time I am keeping a close eye on the chat. Sorry, Jay. When you're sharing your screen, Zoom doesn't notify you of new messages in the chat, which is a little bit frustrating. Okay, cool. In that case, let's continue. Well, this is okay. This solves our problems with confidentiality. However, it might be a little slow because this second box is bigger than the first box. So it'll take a longer time to be transported, and it's just more complicated to work with, right? It would be really nice if we could just use a simple box with one key. So is there a way we can still use that small box? It turns out that there is, because the problem we had before was sending the key to the small box. But now we have a way to send messages with the big box. So we can just send the key to the small box in the big box and then use the small box for later communications. It's faster, it's simple, and everyone's happy. Does anyone have questions about how that works? The bootstrapping the boxes, sort of? Anything that I need to clear up? Any confusion?
Well, okay.
Go ahead.
Not sure if this would apply, but how does one person, say Bilbo, know that it was like Aragorn who sent him the big box with his key originally?
Awesome question. So that is a question of data origin authentication, which I think I'm going to talk about on the next slide.
Oh my God, I'm sorry.
And that's awesome. That's a great question. And it's a question that you absolutely should be thinking of, because it is a pretty big hole, right? If some evil person sends along a box and says, yeah, this box is from Aragorn, and gets Bilbo to put his message in the box, then, you know, Bilbo is going to end up sending his message to the wrong person. That is a question of data origin authentication, which was one of the goals of cryptography that I mentioned back on, like, I don't know, one of the early slides. And yeah, that's a big issue. Unfortunately, because, you know, we don't have a lot of time today, I don't have time to talk about how that works, but it is a really big issue in modern cryptography as well. And there are a lot of structures and systems set up for doing it. So this is the question that Maya brought up. There's still this problem of authentication. The message will be kept secret, assuming that the steps are followed and assuming the box is legit, but it might not be. And yeah, we won't have time to talk about the solution today, unfortunately, but I hope that, you know, in the future, you'll all take a little cryptography and maybe you'll learn about how it works. So does anyone have any questions about this setup, the way these boxes work? We're about to get into the real world, so if you're sick of Middle Earth, then we'll be back to digital world soon. Okay, awesome. Feel free, you know, if there are any lingering questions, feel free to ask or type them in the chat later. No worries. All right, back to the real world. So cryptographers aren't actually wizards in Middle Earth making boxes, though maybe we wish we were. But all of these objects and procedures and structures have real world counterparts. Locking a message inside the box is like encrypting it. It makes it unreadable to anyone who doesn't know the key. Unlocking the box is like decrypting the message. You're undoing the encryption so you can read the message. And this happens all the time on your computer.
I think there's a message in the chat.
Oh, thank you, Belgrade. Curtis asks, can an attacker steal the box and send it much later at a different time? That's a really good question. Yes, it would be possible to do that. However, the attacker can't do anything with the box unless they have the key to open it. So they could create some real confusion, like they could get people to put messages in the boxes and lock them and send them around, but they would never be able to open the box and read the message. So the message would still be confidential, but you're right, it would be a real mess of confusion and authentication. And those are problems that other areas of cryptography seek to solve. Awesome question. You guys are really thinking about this. It's exciting. Yeah, cool problems, right? And really applicable problems in the real world. Yeah, unlocking the boxes like decryption, and the boxes are sort of like encryption and decryption algorithms in the real world. And the fact that there are two types of boxes is not a coincidence in this analogy, because in real world, there are two types of cryptographic algorithms for encryption and decryption. The small box corresponds to a symmetric key algorithm. The symmetric key encryption algorithm, you use the same key. In this case, the key is just like a big number, one of many different types of numbers. But you use the same key to encrypt and decrypt data. Just like with the small box, you use the same key to unlock and lock the box. Public key or asymmetric key encryption algorithms are like the big box. You have a public key, which is not a secret. That's like the top key of the box. You use the public key to encrypt a message. So it's like in the example, you use your top key or your public key to open the box, drop a message in, and lock the box. The bottom key is like a private key. That's kept secret. Only one person should know the private key. And the private key is used to decrypt messages, which were encrypted with the public key. So before I go on to talk about trapdoor functions, does anyone have any questions about this real world setup and how it corresponds to the boxes? Okay, awesome. So the key part, right, in that big box that made it work was the trapdoor. And the trapdoor corresponds to what in the real world we would call a trapdoor function or a one-way function. I'll talk about them a little more on the next slide. Now, the setup at the end, the last construction that we talked about, where you like send the key to the small box in the big box and then use the small box for exchanging messages, that's something that happens in the real world too. Public key algorithms are slow, like the big box. They take longer to run and there's more overhead. The keys are larger. So what you normally do is use them just to exchange a symmetric key, and then you'll use that symmetric key to encrypt your communication afterward. So for example, with HTTPS, when you connect to a website, the website sends you their public key. You send the website your public key, just like this box setup. And then you'll use those to agree on a symmetric key, and the rest of your communication with that website is encrypted with the symmetric key. This is called TLS. All right, we have a question in the chat. Question from Curtis Lee. How do I know the public key from the website is legit? That is a great question. And this is just like the example with the blocks, right? How do you know the blocks actually comes from Aragorn? So the way this works, the TLDR version, is there are certification authorities which provide cryptographic signatures on website owners' public key. And we trust the certification authorities. And we can check to see, okay, the certification authority says that this guy's public key is valid. So this website is indeed what it says. You might have seen this a few times when this goes wrong in your browser, when you connect to a site and you get a warning saying attackers might be trying to steal your information because you have a bad certificate. That's what's going on. So in the Middle Earth example, you could think of the certification authority or the person we trust as being like Gandalf. you could probably trust that the box is coming from Aragorn because it's made by Gandalf, and Gandalf is a good wizard. So yeah, when you connect to a website, that the public key certificate is what tells you the public key is legitimate. Awesome question. Any more questions before we move on to trapdoor functions? Okay, let's move on. So a trapdoor function is a function which is easy to compute one way. So you see in this example, you ask your computer to compute f of x for some x, but it's really hard to invert. So if you asked your computer to compute f inverse of x, it's going to like blow up, or won't blow up, but it'll just take forever and be really slow, and it'll never actually finish. And you'll just have to like cancel the operation, or your computer will crash from working too hard for too long. Sort of. That might be a little dramatic. But the idea is you can compute the function one way, but there's no way to compute the inverse efficiently. Does anyone have any questions about this notion of a trapdoor function? Okay, sweet. So I have a question now. Open question. Is the exponential function, is f of x equals e to the x, a trapdoor function? Any takers? Anybody have any guesses? Anybody just want to take a random guess, typing yes or no in the chat? So remember the notion of a, oh, okay, there are 2 messages in the chat. Awesome. So Jay and Curtis both say no. Anybody, is there anybody out there who says yes? Any takers are saying yes? Okay. So Jay and Curtis, you guys are correct. It is not a trapdoor function because its inverse function, which is ln of x, or the log base e of x, is easy to compute. You just ask your calculator to compute ln of x, and it'll do it in a few seconds at most. Probably do it in under a second unless your number's really big. Great, great answers, guys. Okay. So does anyone know of any real life trapdoor functions? Have any ideas for them? I should guarantee you that virtually every function you've seen in like an advanced functions class or a calculus class is not a trapdoor function, because they're pretty easy to invert. Any ideas for them though? Okay, we have a message in the chat. Maya says, my love life, it only goes one way. Oof, that is, I'm sorry to hear that. But I don't think we can turn someone's love life into an encryption scheme. Sorry, Maya, and multiple reasons for being sorry, I guess. There's one new message, I think. Okay, Zoom chat is acting up a little bit. Sorry, folks. Okay. Well, let's see. I'm going to show you a real life trapdoor function. It's a little complicated, but hopefully we get the idea. So the idea is you have 2 odd prime numbers, p and q, as your input to this function. And the function just multiplies them together. And even if your prime numbers are like hundreds of digits long, your computer can do this pretty quickly, a few seconds, maybe a couple of minutes tops. But this is sort of one way in that when P and Q are really big, if you ask your computer to find the prime factors of this number, just given n without knowing what the original two primes were, it'll take thousands of years to run. And as you make your prime numbers really big, it takes like sort of exponentially longer in time to run. So this is a one-way function. Easy to compute one way and hard to invert. And this is this one-way function sort of is used in the RSA crypto system, which is a public key crypto system that's widely used on the internet today. So does anyone have questions about this one-way function? Anything confusing here that I need to clear up? Okay, cool. So I guess the last question to answer is, if we have a trapdoor function, how do we actually use it in an encryption scheme? Well, it's like the box example. To encrypt a message, you're assuming your message is like encoded as some number, which everything is on the computer. It's a string of ones and zeros, but you'll have to trust me on that. You compute you have a public key and private key pair, and together they define a one-way function. The public key specifically defines a one-way function that you can compute. So you compute if you have a message M, you compute f of M, where f is the one-way function defined by the public key, and the results, the output of that is your ciphertext, your encryption of your message. And because it's a one-way function, no one can compute the inverse unless they have the private key, which gives them some extra information that allows them to invert the function quickly. Does anyone have questions about this? About how trapdoor functions are used for cryptography? Anything confusing? We have a question in the chat. Curtis says, quantum computer when? And Jay asks, what are your thoughts on quantum computing or supercomputers and their effect on cryptography? Great questions, guys. So supercomputers aren't an issue because cryptographic algorithms are designed with, there's this sort of physical limit on the amount of energy it takes to do a computation, and computers are, cryptographic algorithms are designed with that sort of physical limit in mind. So if you have a classical computer, even if it's a supercomputer, it's not going to be powerful enough. There were issues in the past when algorithms were designed for older computers, and as computers got more powerful, you could actually invert these supposedly trapdoor functions with enough compute power. But modern cryptographic algorithms are designed with that sort of physical security in mind, in theory. But a lot of claims in cryptography are somewhat tenuous, so you should take that with a grain of salt. As for quantum computers, they've been, I think the saying is something like quantum computers have been 5 to 10 years away for the past 20 to 30 years. But I think that it would be rather short-sighted, even though, it seems like we're always talking about how they're just around the corner. It'd be short-sighted to count them out. And I'm doing post-quantum cryptography research for my master's. And I think that it's something important to be ready for. Even if it doesn't happen, we'll still be ready for it. Now, great questions, guys. There's just a problem here, though, with all this talk about trapdoor functions. And that problem is we don't actually know if trapdoor functions exist. so all of this stuff I've talked to you about, is it all a lie? Like we don't actually know if these things exist and we're basing the security of our internet and all our communications and our banking on it? Well, it's sort of like a law in science, like a law of physics, right? If you take Newton's laws or other scientific laws, they're believed to be true because we have years and decades of experimental data indicating that they're true. And in this case, with factoring, for example, the problem's been studied for thousands of years by really, really smart mathematicians. And the consensus is that if nobody's found an efficient way to solve the factoring problem, compute the inverse of that one-way function yet, it's probably hard to do.
I have a
But
question.
yes, go ahead, Val.
So this means that quantum computers and supercomputers wouldn't really be a problem. But if a mathematician decides to like find a formula for factoring the prime, then it will be.
That would be a problem. Yeah, I should have been a little more clear about supercomputers versus quantum computers. Quantum computers would be a huge problem because quantum computers can solve these one-way functions because quantum mechanics is really weird and you can factor numbers really quickly on a quantum computer. So yeah, a quantum computer would break all, pretty much all modern encryption that's widely used. A supercomputer doesn't, but a quantum computer would. So sorry if that wasn't clear. But yes, Valerie, you're right. A mathematician coming up with an efficient algorithm for solving one of these, inverting one of these one-way functions would break modern cryptography. All right, so that concludes my presentation. This was just a really brief teaser, and I hope that you got a taste of some of the problems in cryptography. Oh, I see there's a message in the chat. Give me a second, we might not be done. Jay asks, is SHA-256 a trapdoor? The answer to that is sort of. That's a really awesome question. I'm glad you asked. So there's a key difference here, and that is that SHA-256 is not a one-to-one function. So you're going to have many different input strings that will hash to the same value. So you can't really invert SHA-256 in the sense of just like, you can't use it for encryption and decryption because it's not one-to-one. But SHA-256 is believed to be hard to invert. So in that sense, yes, it is like a trapdoor function. It's not exactly the same. Awesome question. But yes, for hash functions, which SHA-256 is, it's important that they be hard to calculate pre-images of, which are sort of like inverses, except there are multiple ones. That's a really, really great question. So yeah, this was just a brief teaser. I hope that you got a sense of maybe what problems in cryptography are like. And I hope that maybe in the future you'll do a little more. You will see more cryptography in Math 135 or 145. There's usually a lecture or two on cryptography. And in fact, if you take Math 145 this fall, one of the profs teaching it is David Zhao, who is a cryptographer. He came up with his own post-quantum cryptographic algorithm, which is pretty cool in my opinion. And real-world cryptography actually uses sometimes silly stories like the one I gave today with Lord of the Rings. They're not as interesting in my opinion because they use Alice and Bob for the characters A and B instead of Aragorn and Bilbo. But yeah, you should know that if you see cryptography, you will be seeing Alice and Bob. I really hope that you had fun and learned something about a cool application in math. At this point, I should also say 3 quick thank yous. One to MathSoc for giving our club the opportunity to do this presentation. One to Maya, who's also in this chat, one of my fellow PMC execs for doing all the promotional stuff. And one to my girlfriend, Valerie, who's also in here. Valerie made all of these cool slides and visuals for this talk because I suck at that. So thank you, Valerie, for making this.
You're welcome.
And we're done. So I apologize this went so long. I was expecting it to be much quicker, but you can now ask me anything about math, the club, Waterloo University, co-op, math careers, Fire away. I'm sorry, we don't have a whole lot of time, but Curtis Lee asks, what is the difference between 485 and 487? Man, okay. So for context, CO 485 and CO 487 are the two undergraduate cryptography courses at Waterloo. They're fourth-year courses. CO 487 talks about applied cryptography, which is all about very practical things like how to, it's a broad overview of modern cryptography and how cryptography is used to solve security problems. CO 485 is theoretical. It's all about the math behind why crypto systems work. That's the main difference. Any more questions about anything? About the club, Waterloo, math, what first year's like, how to avoid geese? Okay, we have a question in the chat. I'm actually going to stop recording now in case people are more comfortable sharing questions when they're not being recorded. So I will stop that. I'm going to stop sharing my screen and stop recording.